In this module, we want to consider one-dimensional motion with a constant acceleration. Even in one dimension, the motion of an object can be quite complicated, but the special case of motion with a constant acceleration is relatively simple and can be very useful. Now, even when acceleration isn't constant, it is often nearly constant over intervals of time with very brief jerks where acceleration changes suddenly to a new nearly constant value. We can apply the approximation of constant acceleration during each interval of time when the acceleration is nearly constant. To begin, we want to start with a mathematical derivation of the equations for motion with a constant acceleration, and this is going to involve some calculus. So, the acceleration, we should recall, is the time derivative of the velocity, and we're going to assume that this is a constant. We can integrate both sides of the equation to determine velocity as a function of time. This is going to be the integral of our acceleration times the infinitesimal dt. And since we have an indefinite integral, we need to add an integration constant, c1. Now, because a sub x is a constant, we can pull it outside the integral. The integral of dt is just t. We know that that's correct because, remember, integration is the antiderivative. So if we take a derivative of our answer, in this case t, with respect to t, we get 1. And that is just the integrand of our integral, so we have the right answer. Now, to determine the integration constant, we can simply evaluate our equation at some specific time. In this case, t equals 0. The acceleration term vanishes because it's multiplied by 0, and that tells us that c1, our constant of integration, is just the velocity at t equals 0. And we'll denote this by v sub x naught instead of by c1. And this gives us our first equation of motion for motion under a constant acceleration. Next, we want to consider the velocity, which we know is the time derivative of position. Again, we can integrate with respect to time. And this will give us the position as a function of time is just the integral of our ax times t plus v naught. Again, it's an indefinite integral, so we have to add an integration constant. We can distribute the integral over the parts which are being summed. The acceleration is just a constant, so it comes out. We have to integrate t dt. The initial velocity is also a constant. It comes out of the integral. And so we wind up, if we integrate t dt, we get 1/2 t squared. Integrate dt, we just get t. And so we wind up with the displayed equation for position as a function of time. We can evaluate this new integration constant again by evaluating this at t equals 0. And we find that this integration constant c2 is just our initial position. And this gives us our second equation of motion under constant acceleration. So these are our two primary equations for motion under a constant acceleration. Position is 1/2 a t squared plus velocity, the initial velocity times time plus the initial position. The other equation is the velocity as a function of time is just our acceleration times time plus the initial velocity. Now we can verify that these are the right equations by doing the reverse of what we just did. We can take a derivative of the position with respect to time. We know that this is our velocity. So if we take a derivative of this expression, well, the derivative of t squared is just 2t. The derivative of t with respect to time is just 1. And so our equation simplifies to being the velocity as a function of time is just the acceleration times time plus our initial velocity. That's just our second fundamental equation of motion under constant acceleration. Once again, if we recall that the acceleration is the time derivative of the velocity, and we take the derivatives, we find out that our acceleration as a function of time is just the constant acceleration. So these are our equations of motion under a constant acceleration, the fundamental equations. And again, t is time. X of t minus x naught, that's just our displacement from the initial position. V sub x of t is our velocity as a function of time. V sub x naught is our initial velocity, and a sub x is our constant acceleration. Now, the equation for position as a function of time is really the most fundamental of the equations. We just saw that we can derive velocity as a function of time by taking a time derivative. So you really only have to remember one equation if you remember how to take derivatives. If you don't want to do that, then these two equations, velocity and position as functions of time, are the two primary equations for motion under constant acceleration. But if you want to, there are a few other equations you can derive from these two, and you can remember these two if you want, but I highly recommend only remembering the first two and deriving the others if you need them. So in the equations listed at the bottom of the screen now, the first two are our primary equations, and you'll notice that in the first one, the equation for position, what doesn't appear in that equation is velocity as a function of time. The second equation is just our velocity equation. What does not appear in that equation is the displacement as a function of time. Now, if we want to take those two equations and, for example, eliminate acceleration between them, then we can write an equation in which the acceleration does not appear. Or we could eliminate the time from those first two equations and get the fourth equation. And finally, if we eliminate the initial velocity, we get the last equation. Gravity gives us a very good example of motion with a constant acceleration in one dimension. As long as you stay within a few miles of the surface of the Earth, all objects will fall towards the center of the Earth with a constant acceleration of approximately 9.80665 meters per second squared. This constant of acceleration due to gravity is usually given the variable little g. The motion of any freely falling object falling vertically in Earth's gravity can be described by the equations for motion in one dimension with a constant acceleration. We simply replace the acceleration term a sub x with either plus or minus g, the gravitational acceleration on Earth. And I say plus or minus because this is a choice. It depends on how you set up your coordinate system. If your coordinates are increasing as the object moves down as it's falling, then we would use a plus sign for the acceleration. If the coordinates are increasing going up, then we would use a minus sign for the acceleration. When solving the free fall problems, our one dimension of motion is the vertical direction, and we will often label this direction as y as a function of time or z as a function of time instead of using the x coordinate. The same equations are going to hold. In the future, when we move beyond one-dimensional motion, it's going to become more obvious why we're making this change of coordinate name. But the important thing is the equations themselves are exactly the same. We're just using a different variable. So now let's consider a problem of free fall in gravity. Consider that we have a balloon hovering 21 meters above the ground. Attached to it is a package, and it's going to be dropped from the balloon at t equals 0. And our question is, how much time does it take for the package to hit the ground? And another question we could ask is, what is the velocity when the package hits the ground? Well, to solve this problem, we're going to be using the equations of motion for constant acceleration. First of all, what are the things that we know? Well, first of all, we know the initial position of the object which is going to fall. It's initially at 21 meters above the ground. Notice that what we've done is we've set the origin of our coordinates at ground level, and we have coordinates increasing up. The initial velocity, we said that the balloon is hovering, so the initial velocity is going to be 0 meters per second. And our acceleration is going to be minus g, minus 9.8 meters per second squared. The minus sign because our coordinates are increasing up, and the acceleration is in the down direction. And finally, the last thing we know is that at some particular time, let's call it t sub g, the package has fallen to the position of 0 in our coordinate system. That is, the package has hit the ground. What do we not know? Well, in our equations, what we don't know is the time at which the object hits the ground. And we also don't know the velocity when the object hits the ground. To solve this problem, well, let's tackle part A first. We use the equation for position as a function of time. We know the initial and the final position, so we know the displacement, which is going to be minus 21 meters when we reach the time t sub g. The initial velocity is 0, so that term vanishes, and so we have on the right-hand side 1/2 times minus g times t sub g squared. This we can easily solve for, and canceling our units here and taking a square root, we find that the time it takes to hit the ground is going to be 2.0695 seconds. And of course, since our initial position had 3 significant digits, and we're just doing multiplication here, multiplication and division, we're going to still have 3 significant digits. But remember, since we want to use this time in another equation, let's not round this number to our 3 significant digits yet. All right, to solve part B, well, we're now going to use the second equation for velocity as a function of time. And the velocity when we hit the ground at time t sub g is going to be minus the acceleration due to gravity times the value of t sub g, which we have just computed. And again, we can easily carry out the multiplications, cancel the seconds, and we wind up with minus 20.2949 meters per second. So this was a very easy problem to solve. When we're working problems, it's going to become advantageous for you to learn how to work more with symbolic variables. I'm sure that most of you are very comfortable plugging numbers into equations to solve problems the way we just did. But again, you really want to work on your skills at working with symbolic variables instead of working with numbers. To do this, you need to hone your algebra skills and you just get some practice. Eventually, when you do this, this will make problem solving much faster, and it's going to yield answers that contain more information and are more versatile. So, to get an idea about how this works, let's rework part A of the previous problem using only variables. All right, so part A of the problem is asking how much time does it take for the package to hit the ground? Again, we know everything in the equation for position as a function of time except for time. So let's take that equation and express it first of all by dividing by the acceleration, then rewriting it as a quadratic equation. The coefficient in front of t squared is just 1. The coefficient in front of t is 2v, the initial velocity divided by the acceleration. And the constant term is minus 2 times the displacement over a, all equals 0. We can use the equation for the solution of a quadratic equation and plug in the values for the coefficients in front of t squared, t, and the constant into that standard equation and simplify to give us the time, which is the solution for at what time we have a particular displacement. Notice that the z of t is the only quantity in there which depends on time. So by putting in various different final positions, we can find the time at which we reach that final position. All right, so if we plug in our particular values for the final position being 0 when t is equal to t sub g, we wind up with actually 2 solutions, plus and minus 2.0695 seconds. Why 2 solutions? Well, the solution with a negative sign corresponds to a different physical scenario. If we had thrown the package up from the ground with just the right speed at this negative time, it would reach 21 meters at t equals 0 and 0 velocity, and then fall back to the ground. Up and down it goes. We can also use this solution for the time at which the particle is at some particular position to solve a different problem. Now consider that instead of hovering, the balloon is moving up at 5 meters per second. Well, we have to change one of our knowns. The initial velocity is now 5 meters per second. Now we can plug values back into the same equation. Now we have more terms that are non-zero that we have to evaluate, but we go through the algebra and we find once again there are two solutions. One is t equals 2.6405 seconds. Notice that's a little bit later than what would happen if the package was not dropped with an initial upward velocity. The package now has to travel a little time up before it starts traveling back down. It takes it longer to reach the ground.